Alright, let's continue what we were doing on Friday. Okay. So we started discussing types of orbits. Alright guys, calm down. We were discussing types of orbits. So in general we have closed orbits and open orbits. Right? We discussed circular orbits, and this is essentially orbits are nothing but you should think about orbits as conic sections. Okay? So closed and open conic sections. The first conic section we discussed was a circle. What is the characteristics which makes it a circle?
It's
What is the property?
in the conic section, it's parallel to the ground.
You said what's the property in the conic section?
What parameter of a conic section makes the conic section a circle?
Are you talking about when the radius is equal all the way around and then like the main point is in the middle, right in the middle?
What is the property? What is that one property which makes the conic section a circle?
The central body being in the middle.
Hmm?
The central body being in the middle.
When you cut the conic section, it's parallel to the ground. Like
That's not the parameter. What is that parameter? What is the parameter of the property?
radius is equal all the way around.
The distance from the center to the edge is equal.
Is it within the parallel?
That is how you get that conic section. But circle, the eccentricity is equal to 0. That is what makes the conic section a circle.
The what is it?
Eccentricity. So we are discussing elliptical orbits. The circular orbits. The main property is which makes a conic section or an orbit circular is the eccentricity is equal to 0. Now we started discussing elliptical orbits. And for this, E is between 0 and 1. It is not equal to 0, it is greater than 0 and less than 1. Okay? So you should always, whenever I draw this, we are going to discuss elliptical orbits quite a bit because those are the most common types of orbits. So this ellipse should make sense to you. So this is the foci. This is the focus. This is the occupied focus. You have the center, and this is where the orbiting body is. Okay? What is this point? Periapsis. This is the apoapsis.
You said the orbiting body is
Orbiting body is always at the focus. If this is your, the central body is always at the focus. The orbiting body Orbiting body is orbiting the section, conic section or the ellipse. So this is the this is where the orbiting body is. Okay. So this is the eccentricity direction. We call this as eccentricity direction or Laplace vector. You remember Laplace vector? C over mu. This is the Laplace direction. It is the direction. It is the line joining the center of the central body and the periaxis. Okay. So and we measure this angle, this true anomaly, from this eccentricity direction. Okay, theta is true anomaly. We'll come across a lot of these anomalies. Okay, we're going to come across true anomaly, mean anomaly, eccentric anomaly. Anomaly is what is an anomaly in the context of orbital mechanics? Huh?
An unknown
Unknown quantity, right? So anomaly is something unknown. But in the context of orbital mechanics, what is an anomaly? What is theta? Theta is an angle. So anomaly is just it's an angle. Okay, it's a changing angle. So what is happening here? The orbiting body is orbiting this ellipse, right? So this theta keeps changing. That's what it is. Got it? Everything else remains the same. This ellipse, the path is going to always remain an ellipse. For a given set of bodies, the orbit is always going to be the same ellipse. If we are talking about Keplerian motion, where we are not changing orbits, we are not using thrusters, no other force is acting apart from gravity, right? We assume that the only force which is acting is gravity. In that case, the body is always going to orbit in this ellipse. What does change? What changes for this orbit? Only this theta. So this r is, we say the position r is this r, right? This is r. So this r is only a function of theta. Okay?
What was F star again? What was F star again?
S star is unoccupied focus. An ellipse will have two foci. The circle will have one focus in the center. This is occupied focus, where the central body S star is unoccupied focus. There is nothing here. It's just and this is also a prograde orbit. We always talk about prograde orbits. Okay? Anti-clockwise. So this should be pretty simple. RP should be a square over mu over 1 plus E, right? Because theta is 0. RA is a square over mu 1 minus theta. Okay? Again, you can arrive at this. Remember the map we discussed, the road map we discussed, Appendix B. I showed you the road map, a picture of the road map, right? So keep that in mind. If you understand that road map, you can derive this. You can very easily derive this. Okay? What is 2A? It's just RT plus RA. Okay, 2A is what? A is this distance, right? A is the semi-major axis. 2A is the major axis. And RP plus RA, this is RP. This is RA.
2A is where?
Two A is this whole thing. A is half of this semi-major axis.
So why do you have A written on that side?
Huh?
You have A written right there.
So if this arrow meets from this distance to this distance, or if you want me to go with this,
Let's look. I see.
this is A.
And the R.
R is changing, R is constantly changing. RP is what? The position of the orbiting body at periapsis. Okay. RA is the position of the orbiting body at apoapsis.
So how does RP change if it's the position of the periapsis?
RP does not change. R changes.
Okay.
So R keeps changing, right? RP is nothing but R at P. Okay. What is the semi-minor axis? This is the semi-minor axis. If you draw a line, right here, semi-major. See this, if you look at this expression, what does it do to you? It answers one of your questions. It answers what is eccentricity. Okay? Do you see that? It answers your question about what is eccentricity. Eccentricity, E. This E. Eccentricity E is what? It is the ratio of, so if you look at this implies E is B over A, or 1 minus B over A square, right? Root of this. Is that correct? You have B over A square.
Yeah.
So it is.
You said the ratio of what?
This is how you define eccentricity. What is this D and A for a square, for a circle?
That's
B
the
is
minus.
equal to A, right?
Yeah. That makes
For a
sense.
circle, B is equal to A. So it is
Oh, 0. It makes sense.
eccentricity is 0. So you can actually derive this just by going through some geometry. Okay? But we are not going to do that. You have to remember this though. Okay. Not for this test, but for midterm you have to remember that.
So what is like, general definition of eccentricity?
Eccentricity is essentially some ratio of semi-minor axis or semi-major axis. It changes for circle and ellipse, you can use this definition. It changes for parabola and hyperbola.
No, I understand it is like mathematical, like what it exactly means.
It means that it defines the shape of the orbit, of the conic section. Shape of the conic section. This is the mathematical definition, and what it means is it defines the shape. So shape means what? Either it is circle, ellipse, parabola, or hyperbola. Depending on how that eccentricity changes, the shape of the orbit changes. Okay?
Does it ever change over time? Does it ever change over time?
What?
The orbiting bodies.
See, that's what I want you to understand, and please, this is a very good question. I just said that, okay? When we are talking about Keplerian motion, what is the assumption? What are the three assumptions? The central body is much larger than the orbiting body. The only force acting on the orbiting body is the gravitational force. Okay? And what is the third one? Spherically homogeneous. Okay? So under these assumptions, the orbit does not change. So it's not a function of time. But in practice, the orbits change. Why do orbits change? Because in practice, the gravitational force is never the only force acting on the orbiting body. Right? I told you there is always atmospheric drag. Even when there is vacuum, there is no perfect vacuum anywhere. There is always some particle. Especially if you're talking about low Earth orbits. So that causes drag. That is a force. There is drag due to solar pressure. There is drag due to third body effects. There is drag due to magnetic force. So if you take into all that, that is not in the scope of Keplerian motion. So for Keplerian motion, the orbit is not a function of time. No cell phones. Okay? So Keplerian motion, the orbit is not a function of time. That's the reason I'm saying the motion is always limited to this plane. And go back and review your Kepler's laws. Kepler's laws are very important. They mean a whole lot than what they just statement says. Right? So if you look at second law, it means that if you really read into it, it will say what I just said. That
Yes, sir.
Alright. One of the other things you'll so you may be asked to prove that what is epsilon here? Epsilon is one of the other things which you may be asked to prove is that prove that the energy of an orbit is only a function of its size. So when Raju asks what is E defines the shape of the orbit. Similarly, A defines the size of the orbit. Okay? So if you have E equal to 0, it's always a circle, but it could be a smaller circle or a bigger circle. That is defined by this A. Okay? And the energy of an orbit is only a function of the size of the orbit. Okay? So when you say energy, you should understand. Just give this a thought. Energy of a closed orbit is always negative. Because the energy is negative, it always stays in a closed orbit. Okay? Energy of a parabolic orbit is 0. Which means it is not in a closed orbit. At the same time, it cannot go out of the orbit. Energy of a hyperbolic orbit is positive. Which means it has enough energy to keep going even after it escapes the orbit of a central body. So if you want to do a flyby, you've heard about flyby? Slingshots. So slingshots are hyperbolic orbits. And at that point, it escapes the central body and it still keeps going. If it does not keep going, if it gets stuck, then energy is said to be 0. That is a parabolic orbit. If energy is negative, it will always be in a closed orbit. It's either
The parabolic has a energy of
0. The eccentricity is 1, but eccentricity is 1, but the energy is 0. So from this, this is just the Vis-Viva equation written by replacing this epsilon with minus mu over 2a. Okay? This is the energy equation of Vis-Viva equation. We have derived this. You can look it up. And finally, the time period is given by 2 pi over root of mu.
What's that over the 2A? What's that over the 2A?
Mu over 2a. This v square over 2 minus mu over r is equal to minus mu over 2. It was epsilon for this Viva equation that this epsilon is replaced by this epsilon. It's called this Viva equation. Yeah. So, can you identify Kepler's laws here? Kepler's first law, this is Kepler's first law for an elliptical orbit. Right? So this is a special case, but you can think about this as Kepler's first law. This is Kepler's third law. What does Kepler's third law say? The square of time period is proportional to the cube of the distance. So T square is proportional to cube of A. And you can also take this, delta A is equal to H over 2 delta T. This is Kepler's second. So Kepler's law specifically apply for, or they are more applicable to closed orbits, right? An ellipse is a circle. Do you agree?
Yes.
An ellipse is a circle with the same semi-major and semi-minor axis. So if it applies to an ellipse, it applies to a circle. Kepler's law was specifically stated for ellipse, right? That is what his first law said, that planets orbit around sun in ellipses. An ellipse is also, a circle is also an ellipse. So if you look at this, you can apply, this is first law, second law, third law.
How's it so?
A circle is an ellipse with A equal to B.
Oh,
When A equal to B, that's a circle. All circles are ellipses, but all ellipses are not circles.
yeah, that's
Right. So a circle is always an ellipse.
circle long.
Circle is just a special case of an ellipse. This is the other definition of the eccentricity. It's the difference between the this is the difference between the foci. Okay. This Ra minus Rp is actually this distance. Okay. Huh?
To the other foci? Okay.
The distance between the foci. If this is Rp, this is also Rp, right? Right? So you have Ra minus Rp is this. Got it? So and Ra plus Rp is this whole thing.
Well, then.
Ra plus Rp. Okay, this is other way of looking at ellipse. Now, this one and this one you have to learn the derivations for this. Okay, so I'll give you the derivations, but
This E is the simplicity for Ra minus Rp over Ra plus Rp. Similar to the E equals square root 1 minus B over A squared.
say it again.
So this eccentricity equation here is similar to the eccentricity equation here.
Yes. It's not the same, but if you calculate, you're going to get the same answer. It's just expressed in different terms. That's it. So this ellipse is actually a very wonderful geometrical shape. You can derive all kind of ellipse and circle. You can derive all kind of beautiful relationships. So you understand what is pi? What is pi?
3.14.
That's bad.
It's the, it's like it's dealing with the circumference of the circle.
Huh?
It's dealing with the circumference of the circle.
It's
It's like a constant for dealing with the circumference of a circle.
Right. It's the ratio of the circumference to the diameter. Okay. And you've heard that the pi value keeps changing, right? Or the decimal places keeps on increasing. What does that mean?
It goes on forever.
So the precision keeps on. Can you really calculate pi? So don't ever say 3.14.
Yeah, it goes on.
Right? And it is just a ratio of so you can define it in terms of ratio of circles, but it exists in every geometrical shape. Pi is also pi radians. What does pi radians mean? Pi radians is an angle which comes out naturally as an answer. Degrees is not so natural when compared to radians. Okay? So you have to try to read about pi. There is so much about pi. It's
Seen the movie Life of Pi? You wrote it to the 100 place. You wrote it.
so there is actually competition where you are required to remember the farthest decimal place of a pi. So there are people. It's
You
that.
said, pi was the ratio to circumference to diameter.
Yes. So how do you calculate the circumference? 2 pi r, right? So what is 2 pi r? That is pi d. So circumference is pi over pi is circumference over d.
So that was like found out with the kind of like experiment because every time you have different circles, different circumference, different radius.
But it was figured out that it's a constant. It's constant every time. So the pi itself is a constant, but we don't know what the actual value of that constant because you cannot. How do you calculate pi? Can you measure a circle?
Yeah,
Make a circle of this string and then split the string.
So that string, every measurement system has something called resolution, right? So what is the resolution of a meter? What is the resolution of your scale? What does resolution mean? How much detail? What is the minimum measurement you can make, right? So if you take a string, you measure it. What is the accuracy? What is the precision you are going to achieve? Depending on the measurement system, right? If the measurement system, if you don't do it that way for actually calculating the value of pi, you do it mathematically. You do numerical integration and try to integrate it to the nth order. Measurement system, if you measure it, the limitation is the measurement system itself, right? The resolution of the measurement system. What is the most accurate clock we have?
The world clock, like a geological clock.
I think I can tell very now.
The best clock we have goes off by a second in 1 billion years.
Where is it?
Huh?
Where is that?
It's not in your iPhones.
It's not even.
So that is again a limitation, right? You see the limitation?
Yeah.
Even the best clock will go off by. You cannot really be accurate.
So we're not living 24 hours every day.
Hmm?
So we're not living 24 hours every day.
That's because time demands.
Alright. So the next one is
Time is completely busy. It's just one dimension of the infinite. I can't deal with y'all. I love you.
next orbit is parabolic orbit. Here the eccentricity is 1. Okay? This uniquely defines the parabolic orbit.
I'll be the most like that. Elon Musk is like equivalent to Iron Man. Is like he's like the John Stark of Tony Stark. Stark Industries. Because he got SpaceX, he got Tesla, he got PayPal.
So is it?
Yeah, and he's like, he's not afraid to take risks.
That's the only thing.
He's supposed to.
Alright. So let's look at a parabolic orbit. This is how a parabolic orbit looks like. Okay. Parabolic orbit is a open orbit. So what happens is, see the velocity direction. You should understand that velocity direction almost becomes perpendicular to the radius vector. You think about this, okay? If this goes on and on and on and on, right? If this parabola goes on and on, it never closes, right? It just keeps going like this. It eventually becomes rectilinear. The motion ceases to be a conic motion and it becomes linear motion. You see that? If you really take this far, it actually becomes linear. Okay? At that point, this velocity, so velocity is perpendicular to the position vector.
What did you say becoming linear?
It becomes rectilinear or linear.
What?
If I take this, the orbit itself becomes, if I take this here, right? So what it will do is, it will become like this.
Oh, that's what you mean when you say.
Yeah, it will become linear. If it goes really, really, really fast. And at this point, when it finally escapes the gravitational pull of the central body, it has no more energy left. The energy of a parabolic orbit is 0. Okay? It has no more energy left to go beyond the escape point. And it is so far away, the gravitational attraction doesn't have any impact on it. So it stays there. The relative motion between the orbiting body and the central body ceases to exist. This is the lost in space problem. Lost in space problem is a parabolic orbit. So you are going nowhere at this point. If you don't have any fuel, you're always there. There is no way you can get out of that if you don't have any fuel.
So you go into
Okay?
oblivion.
And there is something called flight path angle. You have heard about flight path angle as part of your aircraft dynamics as well, right? What is flight path angle? What is horizon?
What is what?
Horizon.
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 Yeah. How do you define horizon?
The sky and earth tension.
Horizon or Verizon?
Horizon.
Why would I talk about horizon?
Yeah, satellites. They got satellites. They deal with space.
Horizon. Why would I talk about horizon?
Because they deal with communications.
Huh?
They deal with communications. So I'm like, I thought it was just like a shit.
Alright, let's talk about horizon. What is a horizon?
The furthest you can see out.
Huh?
The furthest you can see out, longitude.
That is one way of looking at it. It also, you can think about in satellite or in orbital mechanics, what we do is we define something called local horizontal and local vertical. Okay, local horizontal is horizon. Okay. This is the local vertical.
What is?
Okay, huh? That is the local vertical,
E perpendicular?
the perpendicular.
Is that B one?
That is V perpendicular.
Oh, that's the place.
Okay. So how do you exactly define the local horizontal? The local horizontal is the tangent to that point. Okay. And the perpendicular to that is the local vertical. And the angle between the local vertical and the velocity direction is called the flight path angle. That is how your flight path angle for even aircrafts is defined. Okay. If at every point the local horizontal, there is a local horizontal which exists. There is a horizon which exists. Not the horizon you see. That was also a way of looking at it, but there is actually a local horizontal. In your flight path angle, the velocity direction with respect to that local horizontal or local vertical. It is defined with respect to local vertical, but you can also define it with respect to local horizontal. This is local vertical. The velocity direction is not tangential. You should always understand that. Right? Why is it not tangential? If it is tangential, what happens? Even here, the velocity direction is not tangential. Correct? What happens if it is tangential? It spirals in. So it has to, there's always a component where your velocity direction is something like this. There's a radial component, right? If this is your V, there is a tangential component. This component is responsible for opposing the gravity, the radial component. This component is responsible for keeping it in that orbit. This is the local horizontal.
What's the local horizontal?
The horizontal, that is the local horizontal. The tangent to that point is the local horizontal. Okay, and the angle, this angle is flight path angle. Flight path angle, gamma. This gamma is flight path angle. So this flight path angle is positive when you are in the upper half. Okay? When you are in the lower half, this flight path angle is negative.
Is V perpendicular labeled right?
Yeah.
Or is it perpendicular?
It's perpendicular to this. This is the. So we have a radial component and the tangential component. That is, see, that's what this V perpendicular is kind of. It is that component only. It is the same component. Okay. Because it's a parabolic orbit, what happens is, see, this is the radial component, right? This is the vertical component. Okay. So if we substitute this E equal to 1, what are the interesting things we are going to see?
B equals to A.
this is one of the most important things. Energy, because E is equal to 0 or and this, what does this define? This defines escape velocity. Okay. See, escape velocity, we have a, if you look up escape velocity, you may think that escape velocity is one number, right? Escape velocity is a function of where you're escaping from. You understand? So why is this escape velocity?
Why is this?
Right.
Because that's the one that's tangent to the.
See, what this means is
Because.
the energy is just, yes, the energy is just enough to get out of the orbit. Okay? It keeps going, it doesn't get pulled in. It's just enough to go out of the orbit. Alright? Now if I substitute that, I said epsilon is 0, right? If you use this, so combine, look at the Vis-Viva equation, and you substitute epsilon equal to 0, you're going to get this. And from this you can figure out what V is. V is equal to 2 mu over R. So depending on where you're escaping from, you understand where you're escaping from, what that means?
No, you talk position.
Right. You need not escape from Earth itself. How do you want to? How do you escape generally? Hmm? You actually first go into a
Orbit around, right?
You go into something called a parking orbit. Whenever you want to escape Earth's gravitational pull, or if you want to go to Moon, you're not going to go to Moon directly. Why don't you go to Moon directly?
It takes too much energy to try to fly away from the battery. You just kind of sail around and just get. No, I don't know how to explain it, but it's going to take.
See, if you're going to directly, first thing, you don't want to carry all that load, right? You have to let go of that, the boosters, the solid boosters, the rockets, right? So what you do is you go into a parking orbit. From there, you'll fire your thrusters for the satellite alone. So that this position is important. This is the position. At that position, you will calculate what the velocity required is to escape. Okay? And what you're going to do is you're going to calculate what the actual velocity is. And whatever the difference needed, you're going to fire your thrusters to get that difference velocity. You see it? You see it from this equation? Right? So this equation, it carries so much information in just that small this thing, right? You see that? Everybody?
And don't you have to go faster than the speed?
Hmm?
Don't you have to go faster than
So condition what is
the
R?
rotation of the Earth?
R is position.
Like it's in the parabolic orbit?
No, it's not in the parabolic orbit. See, once you're this, what it means is to achieve a parabolic orbit. This is the velocity you need to have. So at this point, see this point, velocity is not 0. When it escapes, velocity is not 0. Velocity is, what is the velocity when for a parabolic orbit?
It's
Velocity is always escape velocity for a parabolic orbit. Achieve that velocity, that escape velocity. This is how you calculate the escape velocity. So at any point, even you can do this from Earth, correct? So what is this R for the surface? It's the radius of the Earth. Okay. Assuming there is no atmosphere, you will have, if you combine the velocity needed to counter the atmospheric drag plus this velocity, you will escape Earth's gravitational pull. If you are on the surface, if you are firing from the surface. Got it? Make sense?
Question, is that why, it seems like a lot of times we see a space, craft go to space, it doesn't seem like it's going straight up, it usually seems like it's kind of.
Right, it goes like this and then it
Starts flying.
So it does that, it goes into a parting orbit and then from there it escapes. So one of the things you're going to notice is, what was V circular?
Dr. Assembly,
Uh-huh.
you said if that velocity is achieved,
Mhm.
then you escape the Earth's gravitational pull. Is that what you just said?
Right.
Dr. Zane.
Hmm.
So if the radius increases, would that mean velocity gets smaller?
Yes. The escape velocity from that point is smaller. So escape velocity, as you go up, the escape velocity keeps changing. Right? You see that from this? If R is, the bigger R is, that means if R is really at parabolic orbit, you should have escaped.
So, okay. What's 2 mu represent?
Huh?
2 mu. What's that?
So it is just this, you keep this 0, you move mu over R on the other side and multiply that by mu. Mu is the gravitational parameter. Okay, so this is your, recall V circular is this. Okay, so what is V escape? V escape is simply root of 2 into V circular. And what this means is, from a circular orbit, from any circular orbit, if the speed is increased by 41%, the orbiting body will escape.
What's the first word? The F?
From a circular orbit, if the speed is increased by 41%, so this implies V escape is what? 1.41, right? V circular. So what that means is, any circular orbit, if you increase the speed by 41%, you'll escape.
Anyway.
Any circular orbit, you consider being in any circular orbit. If you increase the speed by 41%, you'll escape. So if you don't want to escape, you cannot increase the speed by more than 41%. Okay.
Where does that number come from? Where does that number come from?
So this is V circular, right? Mu over R. I substitute this, it will be root 2 into V circular. Root 2 is what? 1.41. 1.41 means 1.41 times. Right? 41% is increase in that. Yes.
So if the escape velocity is the same anywhere on Earth, or does it change depending on where you are?
If you consider Earth as a spherically homogeneous, and if you consider atmosphere as the same, regardless of where you are on Earth, the escape velocity is the same. It's only a function of this R. So you assume that Earth is spherically homogeneous. But that is not, this R It depends on where you're launching from as well. If you're launching from, let's say, up on the mountain, the SAR will be a little more, right, compared to if you're launching from the sea level. So that is, the velocity will vary a little bit, but still it is.
Does it also apply to like the curve of the road when you're driving the car? So if you're driving at a certain speed,
Where do you want to escape? On the road, Rajesh?
I mean, you see, that's what I'm applying. Like, if you increase more than 41, you can like you'll be like out of the road. Does that apply there?
I don't think such a quantity is defined for, unless you're trying to escape from the cops, then probably.
No, I mean, not escaping, but like at least in that car, we're not going to stay in the car anymore. Like to escape from the, I mean, we'll be like away from the road and we'll be like,
This V circular is all specific to orbits. That is, you have to look at vectors, the velocity direction. It may mean something else when you're talking about it.
Dr. Sunday.
Yes.
So why do we launch most of our vehicles from Florida or close to the equator?
I think that's more of a safety issue.
Safety issue.
Yeah, because when you launch, you want to launch off of the shore. You don't want to launch out of here, right? If the launch is not successful.
Oh, I thought it was like more so because it's closer to the equator, like closer to your
Right. That is also, if you really want to launch, see, anything you want to launch in a equatorial orbit, you want to launch closer to the equator, right? To get there.
Is any particular reason?
Yeah,
Wait.
how are you going to get into, see, the amount of fuel you're going to consume to get into equatorial orbit if you launch from the North Pole or South Pole? It's going to be enormous. It's not that you're not going to be able to achieve it, but that's the reason, one of the reasons US has a little bit of problem always launching something in the equatorial orbit because it's way above the equator. And if you want to launch a geosynchronous satellite, any geosynchronous satellite, geostationary satellite, sorry, it has to be always in the equator. And if you want to launch an equatorial satellite or something in the equatorial orbit, you have to do a plane change. So that is actually a very expensive fuel wise. But you can do it. You can still do it. It's not that you cannot do it. Okay, the final orbit is your hyperbolic. We'll finish with this and actually that's an important discussion. I'll talk about that now.
Can we, what, this is important? Can you do this next? Wait, oh, that's
So we'll just finish this. This is the last one. Okay. So the eccentricity here is greater than 1. Okay. So what you have here is you have something like this. So when we're talking about hyperbolic orbits, so this is how strangely enough, your empty focus is on the other side. Okay? Here, in fact, we say this semi-major axis is said to be negative in terms of for a hyperbolic orbit. What defines a hyperbolic orbit? Again, the eccentricity is greater than 1. And what is your energy is greater than 0. Okay? Energy of the orbit is greater than 0. So what happens is, if you have central body is here, the orbiting body comes and it slingshots. Okay? And it keeps going. The relative motion doesn't cease. This delta is called the aim radius. And if you look at what the path, these are the asymptotes. Okay? These lines run parallel, almost parallel to the asymptotes. You know what asymptotes are, right? Lines that don't touch.
What's it from P to the center? What's that from P to the center?
This is the periapsis again. This is the apoapsis.
I'm talking about.
This A.
Yeah, why they both A?
This is both A, right?
Oh, it's the same.
Yeah, because center to periapsis is A, center to apoapsis is A.
What did you say? Delta was the
Delta is the aim radius.
the who rate?
Aim radius.
Oh.
This is your theta infinity. Okay? Theta infinity is one thing. Normally,
What is that? Theta what?
theta infinity. So I would like to point you to something here. We'll try to do problems for this for these types of orbits. But before you guys head out, just to give me a second. I think this book is missing that, but there is a summary section which I'll share with you. It summarizes all the formulas we have derived for different orbits. Okay. What you really need to know is you have to know circular orbits very thoroughly, circular and elliptical orbits very thoroughly. With regards to parabolic orbits, you need to know that energy is, what is energy? Energy is 0, right? What is eccentricity? Eccentricity is 1. So you need to know this table. If you think about it, circle, ellipse, parabola. We have E, right? E is 0, 0 to 1, 1 greater than 1, right? And we look at epsilon, circle it is less than 0, 0, greater than 0. This is what you need to know. For circular and elliptical orbits, you need to know in detail. Or closed orbits, you need to know in detail. Okay? If you learn elliptical orbit, you'll be able to translate everything to circular orbits. The only big thing is this for a circular orbit. Okay? Can you derive this?
Which one? This one.
Yes. Right, they're both, well.
We have derived this.
It's constant, so. They're both constant.
No, they're not constant. It's a function of R. So you try to derive this. Okay?
Not the B circular?
It's actually derived for you guys. You can look it up.
What was the extra credits? I don't think I fully understood it.
How many of you have that? 16, 19. Hang on, let me